I would like to continue off where we left off. So on Wednesday, we left off by writing y as a function of x is equal to C1 sine px plus by C2 cos px. So let me remind you that note small p when we have our small p is equal to the square root of big P divided by EI. The capital P over here is the axial load. Okay, so there is a difference. So what we have just done in equation 2b, we have just written a what? So this is what we call our general what? Solution. A general solution, so basically this function over here in equation 2b, this describe equation 2b. So equation 2b describe a curve like this, okay? So now what we're going to do, we're going to impose a boundary condition to equation 2b, okay, to determine C1 and C2. Okay, so remember we spent a bit on boundary condition. So the boundary condition, as you can see over here, you have all this, by the way. Okay, I just copied from a different section of the notes. You have boundary condition number 1, where when x is equal to 0, y is equal to 0. And then we have boundary condition number 2, when x is approximately equal to L0, y is equal to 0. So I want you to take note y, in case you're wondering why, is the magnitude of deflection. Okay, I want you to take note on that. So we are going to now substitute our boundary condition 1. When x is equal to 0, y is also equal to 0 into our equation 2b. Okay, so this is 0. This is equal to sine or C1 sine 0, right? Why 0? Because if we have P multiplied by 0, right? Then you have plus by C2 cos P multiplied by 0, right? So when this is the case, what we tend to have is we will have what? Therefore, C2 is equal to 0. Okay, let me put a square bracket on the outside here. Or not, you can be confused. Okay, we have C2 is equal to 0. So from here, we can write out y as a function of x. So now we know that C2 is equal to 0. So this one we will get C1 sine px. Okay. And now this is our equation 2c because it was from equation 2b. So the next one we like to substitute is we're going to use boundary condition number 2. Now, take note, you can only use your boundary condition once. Okay, you cannot use the same boundary condition twice. You only can use it how many times? Once. Okay. So that say x is equal to L, y is equal to 0. So this is the condition that we are using now. Okay, as you can see. And then we are going to we're going to put this into equation 2c. So when we substitute this into equation 2c, so y, now our distance, this is L. So this is equal to C1 sine PL. And in this case, we know that this is equal to 0. Okay. So if this equation has to be equal to 0, we have to ask ourselves in what condition, okay, in what condition or conditions where C1 sine PL will be equal to 0. Okay, so in what condition this will happen? So in the condition, so we are going to put the conditions is where PL is equal to N multiplied by pi, okay, where N can be equal to 1, 2, 3, 4, so on and so forth. So when that's the case, sine nx will be equal to what? 0. Okay. So now, I want us to focus now on this expression where PL is equal to what? Nx. Okay. So PL is equal to not Nx, N pi. Now again, this is small p. So therefore, small p is equal to N pi divided by L. So over here, this is our equation number 3. What we are trying to prove down here, just to quickly recap, we are trying to prove, or we are trying to show that, okay, just recap, we would like to show that the critical stress is equal to pi squared EI over L squared A. Okay, and we are almost there. Now you can see where the pi term is from. Okay, so we also know that P is equal to square root what? Capital P divided by what? EI. Okay, and we are going to put this in or substitute P into equation number 3. So now we have square root big P over EI. So this is equal to N pi over L. Okay. So from here, capital P over EI is equal to N squared pi squared over L squared. We are almost done, as you can see, right? So P is equal to N squared pi squared EI, and this will be over L squared. Okay. So one thing, so I'm going to write a term down where PCR will be equal to N squared pi squared over L squared, and then we are going to multiply by EI. Okay. So I want you to take note that PCR is the critical axial load where buckling will occur. Okay. We're not quite there yet. We have to know what is our critical load. Okay. Question so far from anyone? It's real straightforward. Okay. No rocket science, nothing like this. Okay. So the next thing we're going to do, I'm going to copy this equation across. So from here, we know that stress critical will be equal to load critical divided by cross-sectional area, right? So this will be equal to n squared, okay, pi squared over L squared EI over A. Okay. So now, the thing I want you to take note is, note that the second moment of area okay, the second moment of area, I, is also equal to AR squared. Okay. The second moment of area is also I is equal to AR squared. Okay. So we know that R correspond to the radius of gyration. Okay. So if we were to look at this equation over here, R is equal to square root of I over A. Right. So from here, right, we go back to our equation again, or you can rewrite this where R squared is equal to I over A. Fine. Okay. So from here, we are going to let, or in mode 1, buckling analysis, N will always be equal to 1. So what do I mean by mode 1? Okay, so for mode 1, if you have a structure, okay, this is your slender bar, and this is your load P. Okay, so mode 1, where N is equal to 1, your deflection will look like this. So this is where you have your P. Mode 2, you have your load P. This is the other mode. Okay, so a student asked me, it was you, the one from, right? You asked me, right? You asked me, are we just going to look at what sort of deflection, right? So the deflection that we are going to focus down here, okay, is only, we are going to focus on what? Mode 1, i.e. the onset on when buckling will occur. We don't care if it's a S shape or what. Once the onset of buckling will occur, okay, it will